Alright, so we now know how to draw free body diagrams of objects on inclined planes. We know how to break the gravitational force down into components, the F perpendicular and F parallel, and now we've got to do some calculations with this. So let's apply our skills from before to this particular problem. I'm going to model one for you, then you're going to do one as a group. A 10 kilogram box, there's your mass, is on an inclined plane that is at an angle of 20 degrees. That's your theta, with the horizontal. Assuming there is no friction, what is the acceleration of the box? Alright, I've already set up another slide here. Let's click on over there and see how to go about solving this problem. Alright, so we've got our knowns listed, 10 kilograms and 20-degree angle. There's our theta right there. We're looking for acceleration. Let's start by drawing the free body diagram. Zoom in here. We have gravity straight down. We have the normal force perpendicular to the surface. And they said there's no friction. Any other forces acting on that object? No, that's it. So this thing will slide down the inclined plane since there is no friction. It's going to accelerate down in that direction. But these are the only two forces. So let's now tilt our axes. So the positive x direction is that way, and the positive y direction is that direction right there. So are there any forces that aren't along one of those two axes? Yeah, just like we said yesterday, the gravitational force is not along one of those two axes. Fn is along the y-axis. We don't have to break that up. So let's go ahead and do that. Let's break Fg down into its components. There's the component that's perpendicular to the incline. That's F perpendicular. And then there's the component of Fg that is parallel to the incline, which we're going to call Fp. So we've got those two components right there. Fp is parallel to the incline. F perpendicular is perpendicular to incline. Those two are not new forces, they're just simply components of Fg. Alright, so that's all we learned yesterday. Now let's get to the math. You learned in the last video how to find, or what the equation for this and this were. Let's set up a net force equation. Alright, we want to do this. This thing, if it moves, and it does, it's going to move in this direction here. That's the x direction. So let's write the net force in the x direction equation. So this will all look familiar to F net x equals. What forces do we have in the x direction? Only looking at forces in this plane here. Fn is in the y direction. That doesn't help. We don't pay attention to Fg anymore because it's already broken up into its two components. So let's just pay attention to those components. Is F perpendicular in the x direction? No. Is Fp? Yes, and it's to the right. That's the positive x direction. So it's going to be F net x is positive Fp. Anything else? No, that's it. This is the only force in the x direction. There is no friction to oppose that. So there's our net force equation. We're looking for acceleration. So let's start expanding this out here a little bit. Oops, got to change back over here. The net force is mass times acceleration, and that's where our desired value shows up. Fp, I don't know that value right there, but I do know from our last video that Fp is Fg sine theta. So we're making progress. Let's continue here. The mass, we do know that mass is 10 kilograms. The accelerations are unknown value. Fg, we don't know it, but Fg is m times g. So let's expand that out a little bit. And let's finish this off here. 10 times acceleration equals, the mass is 10, acceleration due to gravity is 9.8, times the sine, we're out of room here, back up, sine of, and theta is 20 degrees. This angle right here is 20 degrees, just like this angle. We found out yesterday why those two are equal. We're going to utilize that right now. So that gets us to this point, and at this point I could go ahead and solve and see what I come up with. I have 10 times A equals 10 times 9.8 times sine of 20 gives me 33.5. Divide both sides by 10, that gives me an acceleration of 3.35 meters per second squared. So this object's going to accelerate down the incline at a rate of 3.35 meters per second squared. Alright, same process as last time. We draw our free body diagram, we break force into components, we write our net force equation in the plane of motion, and then we expand things out if we don't know those values. And then we substitute in. Now I do want to show you one more thing before we end this video here. What if we had not been told the mass? What could we have done? Without knowing the mass, could we find the acceleration of each object down the incline? Does the mass affect the acceleration? What do you think? Take a second, discuss that with your group. Does the mass of an object affect the rate at which it accelerates down an incline that has no friction on it? Look at the work above, see what you come up with. Alright, so let's assume that we were not told the mass of the box. Let's assume that the problem only told us the angle's at 20 degrees and there's no friction. What's the acceleration? Let's think through this a little bit more. Let's just kind of redo this. Let's assume we don't know that mass. Well, we'd still set up our free body diagram just like this. We'd write our net force equation. We'd say F net x, sum of the force in the x direction, is F, is Fp. We'd expand that out. M times A equals Fp is Fg sine theta, and Fg is mg. So let's just kind of combine those into that step right there. Fp is mg sine theta. We're looking for the acceleration. We know the acceleration due to gravity, and we know theta. We don't know the mass. But you'll notice mass is on both sides of the equation, so we could divide both sides by m, cancel it out, and we get down to A equals g sine theta. So we could still solve for the acceleration of the box without knowing the mass of the object. G is 9.8, sine of, run out of room here again, sine of, 20 degrees, and that would give you an acceleration of 3.35 meters per second squared. Same answer as before. The mass didn't matter. So pay attention, sometimes you'll see those masses cancel out or something else cancel out being on both sides. If you look back at our work up here when we were told the mass, you might notice that same thing. We have m here, that expands out to m times g, so it could be m times a equals mg sine theta, which is the step we see right down there. And if we're paying attention, we might just notice they canceled out. Instead of having 10 on each side, you just essentially end up dividing out the 10 anyways. Alright, now it's your turn. Work with your group, collaborate together on your whiteboard, solve this problem. We're going to put some friction into the equation now. A 5 kilogram box is on an inclined plane that is angled at 35 degrees above the horizontal. If the box is accelerating down the ramp at 0.3 meters per second squared, what is the force of friction acting on the box? And when you finish that, determine the normal force acting on the box. Good luck, help each other out, do some brainstorming. Everyone should learn together from this. Please offer to help those that are kind of confused. Good luck.